your calculation for C then here? So that's 1 over 4 pi equals 10 to the minus 9, so that's nanofarads. And L is ZO, so that's 600. And that is, let's go 1.2 milliamps. Yep. So that would give us an ideal circuit that looks like this. Here's our source that we want to put into it, and that's designed to be 600 ohm source impedance. There's the input terminals of our filter. We've got 2 series capacitors, output terminal, 1 shunt inductor. Ideally 1.2 millihenries, and I think out of our components box you would get a 1.2 millihenry inductor. But what you'd have to bear in mind there is some of them are tolerance plus or minus 10, some are plus or minus 20. Quite wide tolerance inductors. Yeah. And here we've got to put twice the capacitance value in this here. So you're talking 6.64 NF in each side, and that filter is designed to be connected to a load of impedance 600 ohms. Yep. So your filter circuit is the 3 components within inside the input and output terminals. That's what your load would be. So when you do your practical, you're going to connect a dummy load of 600 ohms. If that's what you're given, it could be 50, and you're going to use a signal generator as an input, and you're going to set its output impedance to 600 ohms. Yep. So on the signal generators, you can select between 50. Alright. So when you do your assignment filter calculations and work and then check them on LC, which we'll look at next week. If I haven't got machines available for you to have a go, I'll at least have my laptop here with LC on. I can put up on the board and show you how it all goes. Alright, because you can start work on assignment next week doing the attenuator stuff anyway. Alright, so what you would then do, they're ideal. You'd then come up, see me or Chris, and find out what we've got for you to achieve those values. So that's the ideal design, and if you could have those exact values, you'd get exactly 600 input and output impedance, and your cut-off frequency would be exactly 40k. Alright, that's if the components had no tolerance, and you didn't have to shift them slightly to preferred values. What you'll find is we'd have a 6.7 nanofarad capacitors for you, so that's slightly above, okay, and we'd have a 1.2 millihenry inductor, I think we have, and therefore you'd have that pretty close, notwithstanding tolerances. The capacitors are at least plus or minus 20% as well. Yeah. So the idea of this is that you then put that in LC, and you can simulate what happens when you change those components to the preferred values, and that's going to shift your cut-off frequency slightly either side of where you designed it to be, slightly either side of 20. Yep. Some of the examples that I give you are close. Some of them are that much further away. All right. Then what you'll do is you'll go ahead and build that circuit and put a variable signal on so you can vary the frequency, and you'll measure input and output across a range of frequencies and make a graph. You can then find out practically where your cutoff frequency is and discuss those results in the light of the components used and the methods used. Yeah. The idea is that filter design software a useful aid to designing a filter and finding out what you might get when you build it. Because you could put component values at all the lowest tolerances and all the high tolerances in LC, find out how the component tolerances could affect your design. Okay. The thing is, in some cases you might get two inductors where this one's 10% above and that one's 10% below, and that kind of partly cancels each other out. Not wholly, because the fact that those two should be exactly the same, if they're not exactly the same, then you're not going to have the same input impedance as output impedance. So it is going to cause some kind of problem. Alright? But tolerances could pull the results back into line, or it could make it worse. Depends. Okay? What I'm going to do now, because I haven't got that software to show you, and I don't know if IT would like it if I think I can put it on this computer, but I don't think they'd like it very much if I did. Alright, but you can get it at home. Well, somehow I'll show you how to use it next week. Alright, because we're going to have a look at the assignment. Again, I'm going to get this printed out for next week, so that you've got it to hand. Right. Title: Design, build and test attenuator and low pass filter to given specification. That's worth 30% of the mark for the module. So the two exams are worth the other 70%. Yeah. That's learning outcome 2. Investigate the performance of two-port networks. Okay. The two-part assignment. So task 1 is write a detailed lab report discussing the design, simulating and testing of an attenuator against a given design specification. And the second task, write a detailed lab report discussing the design, simulating and testing of a passive filter against the design network. Now, this is lab report. So, in terms of how to write a lab report, you might want to refer back to the feedback you got for the lab report from science. Remember the inductor that you did and the capacitor charge discharge? So general how to lay out a lab report, you can get some good feedback from that. Yeah, and do maybe a little bit better job this time than you did the time before. There's always room for improvement. Yeah. One of the things I always say, right, and I always get people go against it, is a photograph of the equipment is not a replacement for a proper circuit diagram. Because the idea of a lab report to the person who's reading it is they might want to repeat your work with slightly different equipment. And so a proper circuit diagram showing where any meters were connected and so on in a normal standard format, it's really important. And every time I say it, still I get some students put a photograph of the setup of the equipment, i.e. they take a picture of it. And I don't tell you very much. No, I'm not saying don't put it in there. I'm saying it's not a replacement for a circuit diagram. Yeah? And that's consistently one I get every year somebody does that. Usually more than one. Alright? So, submission details. I'm going to issue next week, and submission date will be the 6th of November. So there's a fair bit of time because there's practical work to do. The idea is time will be given for practical work to be done in these sessions, Alright, I want to try and not use too much time up, but then beyond that we'll move on to something else and you'll have a bit more time to write up your lab report. Alright, so Dan, how often are you got to be here? Oh, 3 out of 4, because there's an opinion last week you might only be every other week, so... Yeah. Oh, okay, so 1 in 4. Yeah, yeah. Okay. So you'll submit in the usual way as a single Word document to Brightspace. Alright. I've added, this is linked to the Chimandi calculator that we used to attenuate with last week, and there's a link there that you'll have to the Sunny software where you can get the LC filter design. So if you want that, you can be getting that on your laptops and stuff this week. Alright. There's a bit there around rights and responsibilities. There's a grading matrix. Doesn't show very well on this video anyway. Then what we come to is detailed brief. So there's an introduction, okay, and then there's these 7 references against an attenuator specification. So now if you're given number 1, you're going to make an attenuator with a ZO of 600 ohms, V in 0 to 5 volts, V out 0 to 1 volt. And you're also going to make a low pass pi section filter, cut off 18k, impedance 600 ohms. So there's 7 of them, and I'll put your names up against 4 of them. Who have I missed? Kieran. Alright. Alright. So you'll know what your design details are from that table. Okay? And then you can see in the past I've had groups where there's quite a few students who some people are doing the same way. But they might not be using the same set of components and so on, so they'll always get different values. So you're going to design an attenuator to match the given characteristics, specify design attenuation level. Use the calculators. So you do some manual calculations, and you use the Chimandi calculator to check those, and give you an indication of what you're going to get when you change your components to preferred values. So you can't get, like we looked at last time, you can't get 128 ohm resistor, for instance, but you can get 120. So then you'll input the preferred values, and it will tell you, it'll give you an indication of how much your attenuation moves from your design value and how much your input and output impedance will change from design value. We went through that last week. Alright? You'll then build your, and I'm going to assume here that we'll get machines with multi-sim on. If not, I might have to modify this slightly. You build your attenuator circuit on a program called multi-sim, and you can actually simulate an input and output voltage and get some results, and you can measure the input and output impedance circuit using the virtual instruments. Then you'll build that circuit and use an oscilloscope and a signal generator to apply a variety of input voltages and find out what the output voltage is and confirm that the attenuation level is what it is. And compare that with your simulated results on what you designed for. And talk about any differences. And then you'll do virtually the same, in there's an indication of what I expect to see in the lab report, and then you're going to do a similar thing for the filter design. You'll do some manual calcs. You'll do the design in LC. That will give you ideal values that should match your calculations. You'll then ask me and or Chris what values we've got that are close to your values you need. Alright, you'll then put them into LC, and that will give you an indication of how far the preferred value shift you from design. You'll then build that circuit and do tests again to measure the practical cut-off frequency and attenuation of your filter across the range of frequencies. Run your lab report. Alright? So you shouldn't expect this type of filter to be really close to design. If it's in the same decade, you'll be doing well. Okay? Because that's only a constant K. It's the most simple design filter there is, and the roll-off's pretty slow, and so you'd not expect with the type of components you're using to get it anywhere near spot on. But that don't matter, because I realise that your design's not going to be exact. Alright? So you're going to circuit build, you're going to take measurements, and you're going to write a report. I'll issue that to you on paper next week. Right? And that's what I intended to do this week, so we'll finish a little bit early. Okay? We should, I'll be able to tell you when we get here next week, but